tasks. Oh, okay, now we have 2 recordings. Nice. Thank you, Evgeny. Yeah. What I wanted to say exactly. But as I said, LLPs are big, heavy, scary, whatever, require a lot of resources, require a lot of models, a lot of electricity, and require a lot of time. But you can also, for a lot of NLP tasks, you can use much easier, much lighter models. And one of these examples you will meet in Lab 3 and in Lab 2. Lab 2 is mostly about investigating, but you can compare, on Lab 2, you need to compare like how tuning influences on your NLP algorithms, all these things. So simple language models. One of these is N-grams approach. What is the base of N-gram approach? First of all, text is made of units. It's important. Not only letters, but also syllables and words. So like your text can be split in this unit. What is our task in N-gram approach? We are looking, the main idea, we are looking for a sequence of lengths. It's N-gram, sequence of lengths N. And the sequence is N-gram. Like, for example, for this line, 1 gram is, for example, double V, 2 gram is V, like first 2 letters, and 3 gram is VR, like 3 letters together. And the main idea of N-gram, we count how often each N-gram appears in data. We count probabilities. Do you catch the idea? Like, we have a set of N-grams, we have the probability. We got the probabilities. And then, if you have these probabilities, what can you do? You can predict. Like, you can predict what will be the next unit, what will be the next what will the next letter, what will the next syllabus. What, like, you can choose, if you have a probability, you can choose of N-gram, like N-gram is just like several letters together. You can choose, like, most likely what letter and what word appears after the last ones. Yeah. Can you guess, like, did you get the main point of this? You just have a set of probabilities, like, you know that we have this set of letters and the probability of appearance of this set of letters. This is how you can generate. You can, every time you just choose, you can, if you need to insert the unit, you choose the unit with bigger probability. Any ideas from you? Like, you are, now you know this tool. Any ideas where it can be useful? I mean, for what tasks? Yeah. When you type on your phone, then it comes up suggestions. Yes, exactly. Yeah, exactly. Yeah. What do you think? Will it work good for better for shorter texts or for bigger texts? Yeah, I agree, because like short text is okay for this approach, like short context or like some baseline, whatever. But unfortunately, N-grams, they have meaning. If you have like long range meaning, or if you have bigger texts, N-grams become harder. Yeah, they can very fast start to hallucinate. They're not they're not holding the context. They don't know have deep knowledge about the topic you are writing about. But yeah, I like your example very much. Let's go further. Where can you use n-grams? You can use them to detect a language. For example, what can you do? You can build a small model. You don't need a big one. For each of 21, for example, European languages, for this task, you can take about 1,000 characters per language and build n-grams for this. And it will be enough to detect what language is used in this text. Yeah. And if you want to test it, you can take just like test sentences, 10 sentences for each data, count its n-grams, compare to save profiles, and you can decide. Yeah. So the closest profile wins. This is the language. Yeah, this is the main idea of n-grams. Questions? Okay. Next approach is called word embeddings. It's more mathematical, more fancy now. The main idea of this approach is that we turn words into numbers. And of course, we call them vectors. And do you have all the time? Okay. And important point here, you don't just blindly transfer words to vectors. You need to take a constant as well. I mean, like, if words appear in the similar places, like ship, sea, boat, for example, their vectors, the resulting vectors must be closer in space. On previous lectures, you learned about how to detect how close vectors are in multidimensional space. This is the same. Like, for example, apple and orange are close, and apple and car, they are far from each other. Like, logically. Also interesting thing that relations also, you need to, how to say, you need to provide some kind of arithmetics between this lecture, but maybe, oh no, I think I have a slide for this. Yeah. You need to get the main idea. So somehow we need to derive vectors. And in the end, if vectors are close, words are also close. How it works? We will not dive very deep into the algorithms. We will just touch them slightly. We start, first of all, the main idea. We start with one hot. It's like one big vector pool per word. I mean, like you have, you choose a dimension. Like, usually it depends on the task. It's also not a trivial task how to choose a dimension, but luckily this job has been done before you. So what you create? For one big word, you create like one vector per word, mostly zeros. Like, and one. Yeah.
Usually like the size of the vector.
Yeah.
Size of the vocabulary.
Yes, usually it's size of vocabulary, but it can be bigger. It can be a little bit smaller, but like for a simple task, it's like one big vector per word, like the amount of words. How many words do you have? One is zero, like here, you see? Oh, sorry. One is one element of vector is one. Good, but not enough for our task because it's large and it's empty and has quite little meaning. Why it's called word embedding? We want to embed each word into a small vector of numbers. And this number should be derived from the context in text. And as I said, closed vectors, similar words. And there are some mathematical tricks how to pack meaning into fewer numbers. As I said, we have vocabulary, a lot of text. We want to learn vector from every word. We need, when we will derive this vector, we need to look at co-occurrences, what it means, like which words appear near each other, like in a text. And if, for example, also important thing, if two words, they share same neighbors, like many neighbors, as I said, like apple and orange, or like sheep and boat, their vectors also need to be close. And after this training, like first of all, when you derive these vectors, you can use distance or similarity, for example, cosine you learned in previous lectures, to compare meanings. So like the main idea, you choose vectors, you check, like you need to base like on similar words for vectors, and the main idea, if closed vectors, the words are similar or in same context, or far vectors, the different words in different contexts. Yeah. After we derive this vector, we need a fair way to compare these embeddings, to compare these models. And we need somehow to measure quality of our embeddings. Again, embeddings is like we derive the vectors. Now we need to compare the quality of these vectors. And there are two approaches how we can compare these two vectors. First is internal, intrinsic, and external. Let's go like to each example. External or extrinsic, what do you do? You have a set of embeddings, you have a set of vectors, and you use them in a real task. Like, for example, part of speech tagging. What part of speech is this? Or named entity recognition. Then you check metrics like accuracy, and after checking the metrics, you can define if vectors are help in practice or not, or if we created some garbage. And next approach is intrinsic or internal. You can test vectors by themselves. Like, for example, if you want to check like word similarity lists or analogy tests, as I said, like sheep, boat, whatever, coach, and so far. You compute correlation, and you compute correlation with human scores. I mean, like you have result from human, you have result from your model. And this is kind of fast sanity check. Usually, in real task, the key way you do both. You make like some practical synthetic task, and just for some sanity check, you do quick intrinsic side check. So now the question, how we are going to build these vectors. Let's talk about word embedding taxonomy. And usually there are two big families of models. First of all is connectionist models, and it is pure natural neural networks. The main idea you have what do? You learn vectors by predicting words from context with neural net. So you have a neural net, you learn vectors, you predict words. from a context. And one of examples, I think it's in your lab 2, it's World 2 WEC. It's modern transformers you can use. And of course, you have a whole neural network which allows you to learn, which allows you to derive these vectors. You got strong results. You handle rich patterns. Very nice. But they're heavy, and there is another approach which called distributional models or count-based models. The main idea is you built a matrix. This matrix is called co-occurrence matrix, right? Which shows you like which word appears together. We will dive into it. Like now, I'm just giving you an idea. Then you compress this matrix. It's simple, it's transparent, it's fast to train, and it gives quite nice results usually. Yes. Now let's first of all, let's talk about models which are based on artificial neural networks, connectionist models. Like knowledge about vectors, the lives in weights between connected units. We will not dive into it very deeply. It's quite a big topic, but the main idea, like we have input units, you have some hidden layers, you have output units. And there's also a big universe of these approaches. They have many architectural shapes. Have you learned architectures for neural networks before? Somebody learned, somebody haven't learned. Like it can be transformers, it can be recurrent, it can be feed forward. But the main idea, you have this. So like the key idea, you learn meaning by tuning like connections from data. So initially weights initialize in random state, and then you train it. Yeah. But if you don't want to train the whole neural network, you can try to use corpus-based models. And the key idea of this is like you should know a word by the company it keeps. What are we doing? We scan in this approach. We have, like for example, we have a huge set of documents, the huge core corpus of documents, and we just count which word appears near each other. And we build a big matrix, and then we compare it to vectors. And this is a very nice approach because it's also you don't need labels here. You capture like the meaning and connection sorry, from kind of statical patterns in the text. So like simplest idea, you count neighbors. The main base idea, you count neighbors around and then turn it into embedding. Let me just, no, not this one. Yeah, and there is several approaches to this. First is skipgram. We'll talk about skipgram today. It's also okay, how to explain it? Do we have time, or do we need to make? No, we have time. I think skipgram you will use in lab 3, maybe. What? Oh yeah, I understood everything. Yeah. So the main idea, again, we will not dive into it again. It's also based. Okay, let's first of all start with connectionist models. Here, it's one of the model is skipgram. It's first of all the main idea. You got a center word like here, and you predict nearby words. The core idea is. Do you know what sliding window is? Everybody knows. It's like you just have a window which is sliding during your text, and you just take elements which are in these windows. Yeah. What I wanted to say here. So you take like the word windows, you have this sliding window, and you just take all, you have the sliding window, and you take like all sliding windows from this text. Like you show how many word windows form basically this text. Then you'll find the desired word. And for each word, you adjust, like you have a sliding window, you have a words around it. You adjust the weights to the model. So the model, you have this work, and you have like your, sorry, I'm a little bit, in the morning, my brain is not working properly. So you cutted the piece of text with the size of this window. You took a middle word from this window, and you start to adjust your neural model. What do you want? You want your model gives high score to the neighbors of your word and low to the random ones, to all other text. And after you learned your model, so it gives like high score to the words which are near your word and low scores to like some random ones. You take the weights of this model for each word, and so you trained your model, you adjusted weights, and this is your vector. You can take these weights and they become the word vectors. Why is this good? Works to see their neighbors, they are close vectors. Many regularities, many relationships are linear. Like, for example, what I mean here, you see vector of Madrid minus vector of Spain plus vector of France is close to vector Paris. Do you understand why? I mean, like, logically. Great. Yeah. So it's quite fast to train because you don't need a lot. It's unsupervised, and honestly, it works quite nice for many NLP tasks and gives quite strong embeddings. But there is kind of a reverse approach, a continuous back of words. The idea is quite opposite. You need to predict the center word from like context words. Like you have your sliding word window, you have like set of words, and you want to predict what will be between these words. Yeah. So skipgram, as I said, you have center word, you need to predict neighbors, small neighbors, you have neighbors, you need to predict center. So you have a target word, you take words from the window around it. I don't know, like maybe you will take 2 words before, 2 words after. And you need to predict a center window, or sorry, a center word. Yeah. After that, you take each word and you look for their embeddings. You got vectors for each word. And what do? You can sum, or you can find average of these words. And from this vector, like when you summarize like vectors of all neighbors, or like find average amount, a network predicts the target word. Yeah. And if you train it on many windows, on many sliding windows, the embedding will give you real good word vectors. Again, you use weights. Again, it's fast to train. It's stable on smaller data, usually. And again, these regularities like as I said, like Madrid, Spain, Paris relationships, they also keeps linears. So there are, what's the main idea? We have these vectors and we want to we want to mass on these vectors, learn in that way so we can show analogies between vectors, as in the previous example, like Madrid, Spain, Paris. Yeah. Or for example, king minus man plus woman, it equals queen. At least they should be close. Yeah. Yeah, it's working. There are some theorems which are proving that it is working. Yeah. Do you want a break? Okay, we don't have a lot of, yeah. So I can finish. I have a few slides, so we can finish, and after that, you can go home or you can ask questions. Yeah. Another is latent semantic analysis. What is latent semantic analysis? It's called like distributional model, the best one of the best. Now, maybe you have heard about it. It's also quite popular. What's happening here? You have a set of documents, set of texts in your for your model. What's the main idea? You build a matrix, and what you're doing, you create matrix. It's term by document. Like for example, here you have terms or words from each document, and here you have and here you have and columns means number of document. Number of row means number of word in your dictionary, and column means number of document from this. And each row in each cell, what do you have? It's word pattern across document. What it means? How often is this word occurs in a document? Like for example, word 10 appears in document 1 10 times, in document 2 0 0 0, in document 3 1 times, in document 4 8. This is how you build this matrix, term by document matrix. And so each row, it describes a word, how often it appears in document. Each column is presents a document as bag of words, like which so you know about what words are used more often in document, you know what, like in what documents word appears. Good? So, but this matrix is super huge, super big, and super heavy to work with. What do I do? Do you remember SVD decomposition of matrix? When you can decompose any matrix on multiplication of 3 matrices. Somehow, yes, something quick. Yeah. I also will not touch it, but just like trust me, you can decompose your matrix in a multiplication of 3 matrices. Yeah. And what do you do? So you take this matrix and you can decompose it into this matrix, and you can use this sigma matrix, and also you can reduce space of this. Like we will not touch how you are doing, but like you can keep like only top. Yes, for example, you can keep only top singular values from this matrix. So you reduce dimension, you're like fewer numbers, you cut a little bit noise. So you like from this matrix, you take like only highest levels, highest vectors. Yeah. It also allows you to store like higher order relations. Like it's also captures like some indirect links, not just like appear together in the same, but also like kind of indirect links between words. Yeah, and after this approach, like word switch in your for example, in pure metrics, some words may look unrelated. Like in FAT documents, you use the word ship. In other documents, you use the word boat. But like after this approach, they become close, except especially after reducing the space. And yeah, after that, you can use like this small matrix. And a small matrix, and it gives quite a nice results, by the way. For example, it resists model what you get like with this approach. Classic studies, they report that this model achieved like 55% of accuracy on TOEFL synonym questions, like when you need to find synonyms of words. Like, is this word synonym or not? And it's quite high score. So yeah, this is how you can find semantically similar words. Whew. Yeah. LSA, it's super nice and super popular model. Only one thing is problem is SVD. It's heavy. Decomposition of matrices is heavy. It's productivity consuming. Yes, a lot of calculations. And well, researchers are smart. They want to avoid SVD. And one of the ideas is use like random vectors to build the meaning. How it works? Again, we have document. We choose a dimension. So we give each document a fixed, a random, and sparse and ternary vectors. I mean, like each element in this vector will be -1, 0, or 1. So this is how you fill this matrix. And for each word, you sum the random vectors of the documents. Like, I mean, you sum these random vectors of the documents, like context, like where the word appears. We will look an example next time. And sum is embedding. And of course, after that, you can apply and cosine similarity. You choose, by the way, dimension you choose in advance. Usually for small tasks is like between 500 to 2000, something like this. And it's fast. You don't need to do this decomposition of matrices. You don't need big matrices, and it's kind of approximation of LSA. It's not like super clear. It's not super accurate, but quality, if you want like better quality, give bigger dimension and data size. Do I have? Yes, I have example here. So we have these words vectors. So we had in previous slide, we had this we had these vectors for documents, and for word vectors, we want to build word vectors. Initially, we start all word vectors with like it's empty. They all are zeros. Now, important point: each time a word appears a document, you add a document random vector to the words vector. For example, word 1 appeared in document 1 one time. Like, you just take this initial vector and add the value of this vector. What else? Oh, words for example. Do we have it? Yeah, I don't remember how it's word 3. Yeah, for example, word 3 appeared in document 1 3 times. So you just You see -3, -3. This is 1, 1. Maybe it's not this. No, it's this one vector. Like 3, 3, -3, 3. Did you get the main idea? Yeah. To the word, so yeah. And this is how you, for each word, you accumulate like representation of each word in the corpus of document. And this
Question,
actually,
if I may.
sorry?
Can I ask you a question?
Can I see what?
Can I ask you a question regarding what you are discussing?
Of course you can. I try to answer.
The approach you are showing, I don't see where the randomness is because you're still counting how many times a word occurs in a given document.
Randomness appeared here when you create vectors for documents. You feel it's it's vectors randomly. So, like for each element,
you pretend that you saw that word in the document, but you didn't really scan the document to see whether that word was in the document or not. Is that correct?
So initially, for each document, you create a random vector. Kind of random because each element in this vector can have 3 values, like 0, -1, and 1. After that, you start to, and for word vectors, you create 0 vectors first in the first iteration. Then you start to count, you start to scan each document. And if, for example, you found word 4 in the document 1, you just go to this, to this 0 matrix, and you take a vector from D1, and you add D1 to V4. Did I answer your question?
And then the substituted line in V4 does it really reflect the counts or not?
Yes, it reflects the counts because if, for example, word 1 appeared in D4, or maybe we can, okay, let's look towards word 3. If word 3 appeared in D1 3 times, you just add it 3 times. You see, this word, this vector looks like 3, 3, -3, -3. And this is like, this is D1 multiplicates 3.
Okay, I see it now. Yeah.
Okay.
Thanks a lot.
Thank you for your question.
I can add probably here.
Yeah.
So, well, it's not directly, well, in addition to counting if it just appears in a single document, here you collect statistics of word appearing in different contexts. So basically there will be different distribution of, meeting a particular word in different documents. So what you do here, so but by the end, each word vector you can see it as a kind of approximation of the frequency of its appearance in specific documents, so in specific contexts, and this is this you can do because of high dimensionality and randomness of each vector.
Thank you, Evgeny. Any other questions, dear colleagues? Okay. Yeah, thank you for questions. And so yeah, this is the main idea. And surprisingly, reported performance is about like 52% on the same task on this TOEFL synonym questions. Yeah. Another approach is, again, window. Window as in context. In classic LSA and random indexing, like the whole document is a context. You investigate the whole document. I think it's last approach we'll cover today, like just stay strong and you'll free later. So what we can do, we can use like a small window of words around the target word. Like here we have B word. To be or not to be, this is a question. And we want our target word is B. And we take like forward window, towards before, towards after. Nice. And yes, this is forward window for our short phrase. And we learn, like we do the same we did before, but not like from whole document. We learn from words nearby. And the main art here is to choose a size of the word, like small if you choose small, and like size of this word window. It's some local meaning, syntax, phrases. Larger, it's like some broader topic signals. Why it can be useful? You get less noise with this approach. Like the whole document is broad and small, usually small window, it just keeps some more relevant neighbors. And it also helps you to like capture short links between words. Like for example, like verb plus object. This is what you learn. And this works very nice for short texts. Tweets, for example, chat, no big doc. You don't need a big documents to train it, and it's quite easy to train. So yes. So let's go to next task. Yeah, and again, we have this word window, and we just gently slide across the all texts. And you count the co-occurrences inside the window, not on the whole document. Yeah. Yeah, I said about reducing noise already. And yeah, and if, so the bottom line here is like if two words, they occur with similar windows, they end up close in embedding space. How it works? Example. Again, we create this fixed random index vector. Here is our whole vocabulary, and we, but for each word, we create this random vector as we did before. Again, this random vector sparse -1, 0, 1, but for each word, okay? This is our initial situation. And we want to learn about B. What are we doing? We keep, so we have array random indexing, but we add word order here with, in this model. How we do it? We use permutations. So let's look at those examples. It will be last example today. So each vocabulary has fixed random index vector. Yes, -1, 0, -1. You have this AND word window. For target B, it will be not to B, that is. Yes, this is our sliding window and word window. We took 4 words around. And each word is located on each position. This is like, well, this is center. This is like our center -1. This is our center word -2. This is our center word +1. This is our center word +2. Like, and important point, if you want to reach these words, you are moving to the left, just because they are located from the left in the text. They are located in the left. These words are located to the right. So, like you have here, not is left minus. You need to move like minus to left. Your word 2 is 1 left, that is 1 right, is 2 right, like, okay? So like for each word, you detect where it is, what is the position relative the target word be. Is this clear? For everybody? Okay. So this is what's in the left in -2. Okay. And what are you doing? So you have this you have this B, and you take each vector and you permute it by its position. What it means? Let's take for example, not. You see, this is a random vector of word not. And what have you done? Not is in the left from the target word in position number 2. Yes. So what you're doing, you're taking this word not vector and you shift it circularly in two steps. You see, it was like 0, -1. Now you shift it to the left. It's like, have you ever tried like binary rotations of vectors or something like of bytes or shifts of bytes? Have you done it before? No? Okay, I see somebody were doing, some didn't, but whatever. You take this vector and you shift it to left in 2 positions. And you're doing the same with every word. Like for example, 2 will be shifted to the left in 1 position. If you don't trust me, you can check where it is. Yes, it was shifted. You see, 1 was shifted. And I think it's mistake here, by the way. And after that, you just add these vectors. Like after you shifted every vector, like according to the position, left, right, 1 or 2, depends on size of your window, you just add these permuted vectors to the target semantics vector. So like you shift all vectors and then you summarize it with, B vector. Okay?
Maybe, Tatiana, I just want to add a very short link to the next class. So in the next module, so we will see some theory behind this operation. So why does it make sense? So maybe I mean today it's just enough to remain on the algorithmic or computational level. So on the level of operation. So, but you will have some more insight when knowing the mathematical properties of random vectors on high dimensionalities.
Okay, so now it's magic, but this magic works. And you can see that result of TOEFL after this magic is like 78. Nice. Yeah. It also captures like the word order, like who appears for the left, who appears to the right. And it's fast and experimental, and you don't need this matrix decomposition. Finally, very happy. So yeah, this is like when you want order sensitive embeddings. And I think that's all I wanted to share with you today, dear colleagues. Thank you very much. I think I will publish recording from PowerPoint. And do you have any questions? Okay, if no questions, we still have some time till the end of our class. I'm fully yours to answer your question.
Representation, in this latest representation, do the columns have any meanings? Like, are these representing documents or what?
No,
the rows are the words, but the columns are, I don't know. What are the labels?
No, you need to choose dimension.
Okay, so it's just a random number which I pick large enough to have enough stochastic distribution. Let's say
it's not random, but it should be large enough. Yes.
No. I mean, the original vector should be random. Absolutely. So that's the key. I mean, what can be different? So well, here is again. So we will talk more about it later on, but. You can choose to a different numerical system. So here it is an example of ternary codes. So plus, minus 1 and 0. So here you can have a freedom to generate real values or binary values. But what matters is that you generate high dimensional vectors randomly. And again, looking a little bit ahead, so each column doesn't matter. So each position really doesn't matter. So the computations are based on the entire pattern. So you interpret the entire pattern. So you can see. So for example, this matrix below, you can see it as a matrix of embeddings at the end.
Yeah.
So
Okay.
constructed embedding. So and in any embedding, so either it's work to vec or whatever, you do not interpret each and every position. So you just take it as
The interrelations. Okay, yeah. The interpositions rather than
And the important point here is that you see here you do not need to learn embeddings to capture some semantics. And here, but again, here the semantics is assumed to be hidden in the context window, so that nearby words kind of define the word in between, which makes sense in certain case, but of course maybe limited in other cases.
Just one last question regarding the length or the dimensionality of the rows.
Yeah.
Would you envision it pretty much like, I don't know, the how big vectors are in
Yeah.
for instance,
I probably
like the larger the
say again.
better at representing stuff because you don't have too much too many collisions, or you
You
can explain
you think in a totally correct direction. So that's the trade-offs you have to consider. So the larger dimensionality is. I mean, in other words, I mean, in technical words, I can turn this question into capacity property of vectors on certain dimensionality, because here what you do, you sum the vectors up, I mean, for a given embedding. And of course, the longer is your context window, so the more vectors you add, and at the end you want to have them. You want to differentiate between them. So as a rule of thumb, so the higher is the dimensionality, the more stuff you can put inside a single vector, so to say. But then, how large is large? Well, here we are talking about hundreds or maybe thousands of dimensions. And you will see this effect when playing around with random indexing in lab what? 1, yes, lab 1.
Lab 1, yes.
As well as in further in lab 2, when you will also have some vector-based n-gram statistics based classification. So you will feel this effect of dimensionalities.
Okay. Thanks a lot for the clarification. Thank you.
I have a question.
Do you want to ask your question now?
Oh, I can do it after.
Okay, sure. Okay, any other questions related to the lecture's topic? Okay, so dear colleagues, online and offline colleagues, good luck with your quizzes, good luck with your labs. See you on Monday. Enjoy.
Bye. It was like that.